Welcome to our presentation for Experiment 2, Double Pipe Heat Exchanger. This is Group 1, Justine, Lawlin, Julie, and Zach.
Objective. The objective of this lab is to study the performance of a new heat exchanger and the variation of the overall heat transfer coefficient with flow rate.
A double heat exchanger uses heat recovery, an essential of chemical engineers, to transform one energy form to another energy form. Heat exchangers are used in a variety of fields, such as energy, food, chemical processes, and power plant industries. A more in-depth application is the biomass gasification, where heat is both the product and byproduct. Biomass gasification turns solid biomass into gaseous fuel in the absence of oxygen. Double heat exchangers have two pipes, one larger pipe encasing the smaller inner pipe, which will be further explained in the experimental setup and is shown in this figure below. A fluid will flow into the inner tube and another fluid will flow into the outside tube. And this is usually hot fluid in the inner tube and cold fluid in the outer tube. The functionality of the double pipe heat exchanger is used with convection and conduction. Convection allows the heat transfer to be mixed into the stream, and conduction allows the heat to be transferred into the wall. The wall must be thin to have good conductivity. Advantages and disadvantages of the double pipe heat exchanger. The advantages of a double pipe heat exchanger are that they are capable of handling high pressure and temperatures, and its popularity led to easy part sourcing and repairs. The disadvantage of the exchanger is that it is more targeted towards lower heat duties. Leaking can also occur, resulting in error in the production. So to find the overall heat transfer coefficient, you would have to plug in the values that you found into here, where HI is the heat transfer coefficient in the inner tube, HDI is the fouling coefficient for the inner tube, HDO is the fouling coefficient for the outside surface of the inner tube, H0 is the heat transfer coefficient for the annular space, RI is the inside radius of the inner tube, and then the R0 is the outside radius of the inner tube, AI is the inside surface area of the inner tube, A0 is the outside surface area of the inner tube, and ALM is shown in this equation right here. The heat transfer between hot and cold streams is found in this equation, where U is overall heat transfer coefficient, where we need to find A is the surface area normal to find the direction of the heat transfer. Change in TLM is the average driving force for heat transfer, averaging the temperature difference between the two streams, where the parallel flow is shown in this equation, and plugging their inner and outer fluid temperatures into this equation, and then the counter current flow is shown in this equation right here, and then you just plug it in. To lessen the unknown variables of your equation, you can replace Q with this equation, where m dot h is the mass flow rate and of the hot stream, and m dot c is the mass flow rate of the cold stream. The experimental value of U will be used to compare with the theoretical value using the Nusselt equation to find H. So this is for laminar flow, this is for turbulent flow, and this is for the transitional flow. And this is the Nusselt equation that we will have to use to find H, where D is the diameter, the effective diameter, which is equal to the diameter out minus the diameter in, and K is the thermal conductivity of the material. And plugging everything in, we would get H. The effectiveness of the heat exchanger is found in this equation, where Q is what we found in the previous equation, and Q max is equal to C min times THI minus TCI, which is the temperature hot and temperature cold. Okay, so for the C min, we would have to put either the m dot c times CPC or the m dot h times CPH, whichever value is smaller. If CPC and CPH is the same, then we would take the smaller m value and plug into the equation, which will give us the Qmax. The Qmax will give us the effectiveness of heat exchange. The experimental setup is shown here, where the thermometers, the double pipes, the hot water temperature control, the hot water flow in. There's a tank in the back to heat up the hot water or to keep it hot. And then there's a faucet that allows the cold water to flow in into these valves. There's a counter in the parallel, and the counter flows in the opposite direction of the hot water. So this is the opposite direction, and this is parallel with the hot water because the hot water is coming in from this way. And it goes down, and then it exits. And then this is the mid temperature of the hot and cold water. We will be using that in our equation. And yes, this is the flow meter, hot and cold. Yeah.
For the experimental procedures, you first turn on the heater for the water. Then while the water is heating, you calibrate the cold water flow meter by reading from the top of the float. Remember not to run the hot water through the heat exchanger during this time. Set the valves for counterflow using the diagram on the exchanger or TK website. Set the hot water flow rate to a fixed low value and vary the cold water flow rate. And then at each setting, record the inlet, outlet, and middle temperatures of the hot and cold streams when the system reaches steady state. At least 5 cold water readings should be measured. Then you repeat the procedure at a fixed low value for the cold water flow rate while varying the hot water flow rate. Repeat the entire procedure for parallel flow.
Independent and dependent variables. The independent variables are the cold water flow rate and the hot water flow rate measured by a flow meter. The dependent variables are the inlet, outlet, and middle temperatures of the hot and cold streams measured with thermometers.
This is the test matrix for experiment 2. The water heat capacity of the hot stream, the water heat capacity of the cold stream, and the surface area normal to the direction of heat transfer are all given. For the counter flow, you first fix the hot stream flow rate and then vary the cold stream. And then you fix the cold stream flow rate and vary the hot stream. These are the independent variables for the system, and you repeat for parallel flow. The dependent variables are temperature of hot inlet stream, the middle temperature of the hot stream, the temperature of the outlet stream, the temperature of the cold inlet stream, the middle temperature of the cold stream, and temperature of the cold outlet stream.
So for the data analysis of this lab, at fixed hot and cold water flow rate, plot a graph of experimental U versus RED using the equation below for parallel and counterflow using this equation. And using the reference to find the values of H subscript Ti, H subscript Do, and K, calculate H subscript I and H subscript O from correlations of the equations. This is equation 5, equation 6, and equation 7 from the lab guide. Also, plot the effectiveness of the heat exchanger for both parallel and counterflow as a function of RED, making sure to use the calculated Q from the following equation, and discuss the limitations of equation 5 and 6.
Some safety concerns to be cognizant of is that the metal might be hot due to the hot water. Wear goggles and lab coats to prevent any water damage to your eyes and to your body. Make sure you have a mop and a bucket nearby, just so that you can clean up the water spillage if there are any, so people do not slip. Wear closed-toed shoes and keep your desk area clean for the pump so that it can have ventilation.
And these are our references. Thank you for watching.